Hello everyone, my name is Finding Pepper, and welcome to the very first episode of How to Code a 3D Game in Scratch. In this episode, we'll code a wireframe renderer, which can render all sorts of objects and scenes, such as this cube right here, in real 3D, using lines connecting up vertices. I'll cover 3D projection, camera movement and rotation, and Z-clipping, which just ensures objects don't do this when you run into them. And I'll explain each concept in detail, so hopefully by the end of this video, you'll have a sound understanding of the basic math behind 3D rendering. In future episodes, I'll cover topics such as making solid faces with the triangle fill algorithm, backface culling, collision between 3D objects, and more. But without further ado, let's begin. I'd also like to give a huge shout out to Math, who has an amazing 3D tutorial on their Scratch account, which this tutorial is largely based on. Now, at least for this episode, we'll be using lines to draw everything, so I think a good place to start is to make a custom block to draw just one line, and then if we want to draw a bunch of lines, we can just use the block a bunch of times. Let's call this block Draw Line From, and then some inputs for the start of the line. Remember, in 3 dimensions, our coordinates have 3 numbers. X is left-right, Y is up-down, just like we're used to, and the new Z dimension can be thought of as forward and backward. So, back to our block, we'll need 3 inputs for the starting position. X1, Y1, Z1, 2, X2, Y2, Z2. Make sure to check the Run Without Screen Refresh box, which ensures everything inside the block runs instantaneously, or at least as fast as possible. We're going to use the pen extension to draw everything, so go ahead and add it now. Let's start simple, and just go to X1, Y1, pen down, then go to X2, Y2, pen up. So for now, we're just disregarding the Z position completely. This actually has a name. It's called an orthographic projection, and it's used in some 2D games. We'll leave it like that for now, and go ahead and write some code to draw the lines of a cube. Make a block for this as well, so our code stays nice and organized. I'll call this block Draw Cube. Run without screen refresh. Start by erasing all, and set pen size to 2. Cubes have 12 edges, so we'll need to draw 12 lines. We'll start with the lines on the front square, which I'll place at a z of 6. So draw a line from -1, -1, 6 to 1, -1, 6, then -1, -1, 6 to -1, 1, 6. And then duplicate those two and change the 2 -1s for the first position to +1. And those 4 blocks draw the front of the cube, so let's duplicate those to draw the back face. That one will be a little bit behind the front face, so just change all of the z of 6 to a z of 8. And everything else will remain the same in those. Then finally, we need to draw the 4 lines connecting up the front to the back. The starts and ends of those will have the same x and y values, but the z values will be different. The start will all be 6, and the end will all have a z of 8. The x and y's of these, the first one will be -1, -1, then -1, 1, then 1, -1, and then 1, 1. Lovely. When the flag is pressed, trigger this block in a forever loop. Now, what wonders has all our hard work led up to? Run it, and we get a tiny motionless dot. Wow, so exciting! Okay, so this looks decidedly not 3D, and not cube-like, but I assure you it secretly is. And to see that, all we've got to do is to change our orthographic projection script to perspective projection, which takes into account the Z dimension. Now, if you've done anything with parallax, or even if you've just looked outside, which I haven't, but maybe you have, you probably know that things farther away look smaller. To be precise, something twice as far away looks half the size. So we should divide the point's x and y coordinates by its z value to make the projected coordinates smaller when the point is farther away. So replace our goto x1, y1 with goto x1 over z1 and y1 over z1. And then we'll do the same thing with x2 and y2, dividing each by z2. Now if we run this, it still looks like a tiny dot. But don't lose hope yet. We're very close to seeing our surely beautiful cube in all its cubic glory. What's really happening is that it's just rendering really small. To fix this, we need to multiply our projected coordinates by a constant known as the focal length. The focal length controls how far away things look, as well as the field of view. Let's create a variable to hold it, called focal length. Because we're only using one sprite and no clones, it doesn't really matter whether you make variables for this sprite or for all sprites, but since this value is really only used in rendering, I'll make it for this sprite. When the flag is clicked, set this to 400. This number is arbitrary, but I think it works quite well. Back in draw line, we'll just multiply all the inputs to goto by focal length. Like so. Try out the project, and voila! Finally we can see the cube. But this is still pretty boring. We can't even move around. So let's add that now. Create variables for all sprites called camera X, camera Y, and camera Z. These hold our camera's position, or in other words, where we're viewing the world from. Set these to 0 when the flag is clicked. Then create a block called moveCamera. Run without screen refresh. This block will allow us to, shockingly, move the camera. Inside, we'll want to change our camera variables. Let's start with camera X. Now camera X is left to right, so let's use the D key to move right and the A key to move left. Now we could use if statements and check if key D press change camera X by 1 or whatever, but we can actually do this a lot more easily, because you see, when Boolean values, that's either true or false, when they're put into number inputs, they return either 1 or 0, and we can use this to our advantage. If we write key D pressed minus key A pressed, then this will give us 0 when we're pressing no keys, 1 when we're pressing the D, and -1 when we're pressing A, because we're subtracting key A pressed. So this gives us a really easy way to change our camera position based on the user's input. Now this will change it by a quite significant amount, so let's just divide it by 10. Now duplicate this for the camera Y. I'd love to use the space and shift key to go up and down, but unfortunately we can't detect the shift key. So we'll have to make do with the E key for going up and the Q key for going down. Then finally duplicate this for camera Z, and here we'll want to use W and S, so key W pressed minus key S pressed. Alright, that's moveCamera done for now, but how do we take this into account when rendering? Well, you can see in this example that when we move right, our world appears to move left, and vice versa. We'll take advantage of this and essentially shift our world in the opposite direction to the camera's position before rendering. This gives the appearance of the camera moving, but really the world itself is moving around our camera. Now back in draw line, to make our code a little bit cleaner, especially later on, let's make variables to hold our transformed X, Y, and Z positions. The transformed positions will be what they are after moving them based on the camera position. These variables will be for this sprite only. I'll call them x1, y1, and z1, and x2, y2, and z2. Alright, we'll set x1 to the x1 input minus the camera x, like we talked about. Then set y1 to the y1 input minus camera y, and set z1 to the z1 input minus camera z. Now duplicate these and change all the 1s to 2s, so x2, y2, and z2. and make sure to change which inputs they're referencing as well. Then in the goTo blocks, we'll replace the references to the custom block inputs with our transformed position variables. So basically just replace all the pink inputs with their corresponding orange variables. Alrighty, try this out and we should now be able to move around. This really helps show how the cube is actually 3D. Now you may notice some of the lines getting a bit warped or squished. This happens because of Scratch's built-in sprite fencing, which prevents sprites from moving off screen. There's actually a really easy way to disable this, and that's by setting the size to infinity. When flag clicked, set size to 1 divided by 0, which resolves to infinity. Keep in mind this is only possible because our costume is infinitely small. Alright, this looks a lot better. If we try to go past the cube, though, everything gets wonky. Rest assured we'll fix this by the end of this video. But first, let's finish up our transformations by adding rotation. This is arguably the hardest part of the video and will require a fair bit of trigonometry, so bear with me. Let's start simple by adding 2 new variables to hold our camera's horizontal and vertical rotation. I'll call them camera rotation horizontal, and then I'll shorten this name to just camRotH. And then we'll also make a camRotV for vertical. Set these to 0 when the flag is clicked. Now you might be thinking to yourself, why not just call them X and Y? Well, I find that a bit more confusing because left-right rotation is actually called Y rotation, because when you rotate left-right, you rotate around the y-axis. Likewise, X rotation is up-down, and I think it's more intuitive to just stick with horizontal and vertical. Now in Move Camera, we'll change our camera rotations in the same way that we changed our positions, using the key pressed minus key pressed technique. Change camera RotH by left arrow minus right arrow pressed. Now we want to do this in a little bit bigger increments because there's 360 degrees in a full circle. So let's change the divided by 10 to a times 5. Now duplicate this for camera rotation vertical. And this one will be up arrow pressed minus down arrow pressed. Again multiplied by 5. Let's also limit our vertical rotation so we can't look higher than straight up or straight down. I'll just check if camRotV is greater than positive 90, and if so, set camRotV to 90. If camRotV is less than negative 90, set camRotV to negative 90. Alright, now to do the transformations, we're going to need some trigonometry. So before we get coding, let's briefly review our basic trigonometric functions, sine and cosine. Imagine a circle of radius 1 and a point on that circle. Say we know the angle that point is at in relation to this rightward horizontal line, which is typically where 0 degrees is on a circle. Let's call that angle alpha. Say then we want to know the x and y coordinates of that point. Well, it turns out that cosine of alpha is just the point's x-coordinate, and sine of alpha is its y-coordinate. If the radius of the circle wasn't 1, all you'd have to do to find the x and y coordinates would be to multiply cosine and sine by the radius of the circle. You'll notice that increasing the angle would move the point counterclockwise. This is the standard within mathematics, and it's what we'll be using within this project. However, it can be a bit confusing because for some strange reason, the built-in Scratch direction is opposite. Now we're going to be using the sine and cosine of the camera rotation many times per frame, and they take a lot of time for the computer to calculate. If we're drawing a lot of lines, this can really slow our project down. But since our camera rotation only changes once per frame, we can simply calculate these sine and cosine values once and store them in variables right after we rotate the camera. I'll make a block for this called calculate trig values. run without screen refresh, and then put it right after move camera. Then I'll make 4 variables for the sine and cosine of our rotations. They will be sine h for sine of horizontal, cos h, sine v, and cos v. Then in calculate trig values, we'll just set each of these to their corresponding sine or cosine. So we'll set sine h to sine of camera rot h, cos h will be cos of camera rot h, sine v will be sine of camera rot v, and cos v will set to cosine of camera rot v. And just to be clear, cos is short for cosine. Now, like with camera movement, when we rotate the camera, we want to instead rotate the entire world in the opposite direction. We'll handle each of the 2 axes separately, but it's the same formula for each. For each one, the object rotates around an axis. This means that the coordinate corresponding to that axis won't change. For example, if we rotate around the y-axis, the y value will not change. Hence, we can think about this problem in 2D. Let's start by figuring out how to rotate a single point left by a certain angle. We know the point's position. Let's call that xy. We don't know the distance between our point and the camera, although we can find it if we need to, so let's for now just call that d. Then we'll call the angle we want to rotate by theta. We'll call the position after rotation x2, y2. That is what we want to find. Now, it's not immediately clear how to go about solving this, but when dealing with angles and circles, trigonometry is a clear starting point. So let's try writing our coordinates in terms of the trigonometric functions sine and cosine. To do that, we'll have to write in one more angle, which we don't know yet, which I'll call alpha, which is the angle to our starting x and y. We can write those starting x and y coordinates in terms of sine and cosine of alpha. And remember, we multiply sine and cosine by the radius of the circle, which is d. For x2 and y2, the angle is the sum of alpha and theta, as you can see. So we need to find the sine and cosine of alpha plus theta. Now, we don't know alpha, but we do know the sine and cosine of alpha. They're the starting x and y. And it just so happens that there is a way to write the sine and cosine of the sum of 2 angles in terms of the individual angles. You can see those formulas here. They are known as the angle sum identities, and they're pretty large and can seem quite intimidating. I don't expect you to know why these formulas work or how they're derived, but if you're curious, I'll link a proof in the description, which I encourage you to check out. Now, if we multiply both sides of each equation by d, we start to get some values which match values we have in our scenario. We can substitute those in, and suddenly we have a much simpler equation. The values we want to find are now written entirely in terms of values we know. That's x, y, and theta. This is awesome! But this is for rotating by a positive angle. We want to rotate in the opposite direction of our camera, so really we need to rotate by negative theta. Luckily for us, the negative angle identities, as they're called, are really simple. Sine of negative theta is negative sine of theta, and cosine of negative theta is equal to cosine of positive theta. If you think about it, negating the angle is the same as flipping over the x-axis, which changes the y-coordinate, so the sine, but not the x-coordinate or the cosine. Using these identities on our formulas essentially just flips the plus and minus, as you can see. Alright, it's now time to put these formulas into Scratch. In drawline, after we transform by the camera position, let's begin transforming by the camera rotation. We'll start with x1. Set x1 to z1 times sine h plus x1 times cos h. This is the formula we just discussed, by the way. Then set z1 to z1 times cos h minus x1 times sine h. Now you'll notice that when we set z1, we refer to x1. However, we want to refer to the value of x1 before it was set in the block above. The easiest way to achieve this is to make a custom block which sets all three simultaneously. Call this setPos1 to, with inputs x, y, z. Inside, simply set x1 to x, y1 to y, and z1 to z. I'll make another one for pos2, called setPos2 to x, y, z. You can just copy the code for setPos1 and change the x1, y1, z1 to x2, y2, z2. Just like that. Now back in drawline, we can use this block, setPos1 to, then move what we set x1 to into the first input, and then move what we set z1 to into the last input. The middle one is for the y, but we don't want to change the y, so just put in a plain old y1. Now let's duplicate this for pos2, and we'll just duplicate each of the formulas, changing each of the 1s to 2s. Make sure you've got them all, and if you do, we can try this out. Using the left and right arrow keys, you should now be able to rotate the camera left and right. We still can't do up and down though. Before we do that, let's take a moment to use our setPos1 and pos2 blocks to do the transformations for camera movement as well, just to make our code look a little bit cleaner. So up at the top, setPos1 to, and then move the camera position transformations into those inputs. And then do the same for pos2. x2 minus camera x, y2 minus camera y, and z2 minus camera z. Lovely, now our code looks a little bit nicer. And let's get on with the vertical rotation. The formulas are going to be the same at heart, but we're referring to a different angle, and we're referring to different axes. So setPos1 to, and here for vertical rotation, we're rotating around the x-axis. So for the x position, we'll just use our plain old x1 variable. Then for the y, we'll get a minus, and set it to y1 times cos v minus z1 times sine v. Then for the z position, we'll set it to y1 times sine v plus z1 times cos v. Again, duplicate these for pos2, changing each of the 1s to 2s. Alrighty. That should be our rotations done, so let's try this out. And there we go. We can now rotate left and right, and up and down. Now you'll notice that we can only move in one direction, not in the direction that the camera is pointing. I think it would be nicer to change it so that we move in whatever direction the camera is facing. So in Move Camera, let's replace our Change Camera X and Camera Z with something involving the horizontal camera rotation. Let's start with moving forward and backwards, so that's the W and S key. For our forward and backwards movement, we can imagine the unit circle rotated left by 90 degrees. That way, 0 degrees will be pointing straight up or straight forward. Then, to get the left-right change, that is, the change in X, we'll just need to multiply the amount we want to move by the sine of our camera angle. However, we want to be moving left by the sine, not right, so we need to negate the sine. Then for the z change, we'll just multiply by the cosine of the angle. So let's put that into Scratch. Change camera x by key W pressed minus key S pressed over 10 times negative sine h. Then change camera z by that same key pressed times cos h. Now for the left and right movement, we can imagine a more traditional unrotated unit circle with 0 pointing out to the right. Then the change in x will be multiplied by the cos of h, and the change in z will be multiplied by the sine of h, just like we're used to. So in Scratch, change camera x by d pressed minus a pressed over 10 times cos h. and then change camera Z by the same key press times sine H. And then we'll leave the Y the same because we don't want to take vertical rotation into account here. Alright, let's try that out. And now we move in the direction that we are facing, which is quite a bit nicer, I think. It is now time to fix the issue of trying to move inside the cube. What's happening is that the renderer tries to draw lines which are behind the camera, but those lines shouldn't be drawn. Fixing this isn't so simple as just not drawing the lines which go behind the camera though, because some lines are only partially behind the camera. To deal with these, we need something known as z-clipping. This is the process of clipping lines, so only the part in front of the camera is drawn. This horizontal line here represents what is called the near clipping plane, which typically lies just in front of the camera. Nothing behind this plane should be drawn. Say we have a line that is partially behind the near clipping plane. We need to clip or remove the part of the line which is behind the plane. To do this, first we need the percent of the line we want to clip. That's the percent that's behind the clipping plane, and to find it, we can just look at a single axis. Take the difference in z values between the endpoint and the plane, that is clip z minus z2, and then divide that by the total difference in z values over the whole line, that is z1 minus z2. Now the clipped z will just be that of the near clipping plane. To get the others, we can just decrease the values by the percent we want clipped multiplied by the total change in that axis over the whole line. Alright, back to Scratch. Let's create two new variables for our z-clipping. The first will be the near clip plane, for this sprite only. I'll set this to 0.05 when the flag is clicked, so that's just very slightly in front of the camera. Our second variable is clip percent, and we'll use this in drawLine. In drawLine, after we transform our positions, let's set clip percent to 0, indicating that by default we don't want any of the line to be clipped. Then let's check if z1 is less than near clipping plane. If so, we want to clip off vertex 1. So set clip percent to near clipping plane minus z1, that is the distance from z1 to the near clipping plane, over z2 minus z1, that is the total change in z across the line. Then we can change the position of vertex 1 just like we talked about. Set pos1 to, for the x it will be x1 minus, then x1 minus x2 times clip percent. That is, we're decreasing x1 by the percent we want to clip multiplied by the total change along that axis, which gives us the percent we want to clip in that axis. Then do the same for the y input. Put in y1 minus y2 times clip percent. Then the z will just be that of the near clipping plane. Now let's duplicate this for if z2 is less than near clipping plane. In this case, we'll want to just switch out all the 1s for 2s and all the 2s for 1s. This can be pretty easy to mess up though, so I'll go over everything. Set clip percent to near clipping plane minus z2 over z1 minus z2. Then set pos2 to, then the first input is x2 minus x1 times clip percent. Then the second input is y2 minus y1 times clip percent. Then the third input is near clipping plane. Okay, now finally around where we actually draw the line, let's check if clip percent is less than 1. So if the entire line has been clipped, we don't draw it. Try that out, and you will see that no issues occur when we try to go past the cube. Everything looks wonderful. You can see our z-clipping in action if you look at the lines from just the right angle. And this is our wireframe renderer done. We've coded quite a lot of advanced things in this video, so congratulations on getting this far. I know this hollow cube might not seem too exciting, but you could use this render for really any sort of 3D scene you wanted to view, and you could easily modify those scenes in real time. I'd really love to see any games you make with this, and like with my other tutorials, I'll create a Scratch Studio for projects made with this tutorial, which I encourage you to add your projects to. Anyway, I hope you enjoyed this tutorial, and I hope to see you in the next episode where we will cover the trifill algorithm. Have a great rest of your day, and goodbye!